So let's have a look at classification metrics and machine learning. So along the way, we'll introduce the concept of machine learning, and then we'll look at some of the classification metrics that we can use to be able to determine whether we're successful or not. And in cybersecurity, we often use the concept of true positives and false positives, and then base our metrics on those evaluators. And then at the very end, we'll have a look at some numeric and categorical prediction. Okay, so what is machine learning actually? How can we classify machine learning? Well, the first type that we have is supervised learning. And with supervised learning, we can either have regression methods, which will predict numeric values or based on numeric features, or we can have classification such as hot and cold. So a classification often involves us defining categories for things. So with supervised learning, we take a training set and then we label it. So it might be a data set that relates to whether someone has diabetes or not. So we would take all of our data elements, our attributes, such as blood pressure, BMI, age, and so on. And then at the very end of the data set, or one of the columns, attributes of the data set, we'd add in whether someone had diabetes or not. Then with this, we can train a model to be able to look at a new instance and then define the classification for it. So typical methods that we might use here are support vector machine, SVM, and logistic regression. We might also want to predict numeric values, such as the number of logins over an hour. For that, we can use the regression methods, linear regression, decision trees, random forests, and k-means neighbours. For this, what we have is we have numeric values, and we use the training set to be able to train on the expected value or the real value. And then when another value comes in, we can make a prediction on a certain attribute or feature. The other type that we have is what's called unsupervised learning, and in this we don't actually classify the data, but we allow it to be able to naturally congregate inside clusters, say, or we can reduce the complexity of the data by reducing the number of features that are used to be able to train. So examples of this are in clustering. So with clustering, we take our data sets and we move them into areas where they naturally cluster together. If we were to draw two features, one feature against the next, then we might see our data moving into certain clusters. In this way, we can have unsupervised learning. Another type that we often use in cybersecurity is anomaly detection. So with this, we might have clustering to find where the normality is, and then when something comes along which doesn't fit into any of the clusters or into our normality, we would see this as an abnormality or an anomaly. And then we can use semi-supervised, and that's where some of the data has been tagged and other data is not. And then we get reinforcement learning, where the machine can take an action, can observe, and then can try and improve or not. So in this case, it will assess whether it's been more successful or less successful, and then change the action based on that. Okay, so one of the metrics that we have is what's called the confusion matrix. So with this, we have classifications. So true positive is when we have correctly identified something that we want, we've classified something that we want it to be classified as. So that might be the detection of malware. So if we have malware and we've detected it correctly, that's a true positive. Then we have what's called a false positive. With a false positive, we generate an alert or a true, but it's not actually the truth. In this case, it might be that we think that device is infected with malware, so that would alert a positive, but it's not actually infected. This is what's called a type 1 error. Then we have what's called a true negative, where we reject something that is actually a negative. So that's a good thing. So if it was if a device wasn't infected by malware and we made the judgment that it wasn't infected, then that's a true negative. And then the next type of error is what's called a false negative. In this case, we've dismissed something, but it's actually true. Okay, so we've actually missed. So the device is, say, infected by malware, but we identify it as false, not having malware. So we can draw what's called the confusion matrix. So this is the actual values. So let's say this is the positive case, the thing we're trying to detect, and this is the negative case, things we're not trying to detect. And then we make a prediction. So if we identify something correctly, and it's actually correct, then that's a true positive. For the negative, and we also identify as negative, then we have a false negative here. The two types of errors that we have are the false positive and the false negative. So what we typically do is that we'll gather together for our data set all of the true positives, false negatives, false positives and true negatives together. So it might be that we take a data set of 100 data points, and it might be something that was infected, a device infected by malware. So let's say that out of 13 positive devices infected by malware, we identify 10 positively correctly, and then 3 we miss. And then over here we have a false positive. In this case we have 5, and then the false negatives are 82 here. Okay, so if we add up, then we should get a data set of 100. The main metrics that we would use in cybersecurity are precision, recall, accuracy, and the F1 score. The precision is equal to the true positives divided by the total of the true positives and the false positives, this value here. So in this case we've got 10 divided by 15, we get 0.67. The recall is the number of false negatives added to the false positives divided by the total in the data set, and in this case we have 0.13. Then we get the accuracy, which is the true positives plus the true negatives, true positives plus the true negatives divided by 100, and that gives us that score here. And we also get the F1 score, which is the precision times the recall over the precision plus the recall. For all of these metrics, we want as near 1.0 as possible. So we define our confusion matrix like this. So here is predicted no, and no, and here is predicted yes, and yes. So we end up with a confusion matrix, and we want to make sure that we maximize these two values here and minimize these values. Some of the metrics that we can also use: sensitivity, prevalence, miscalculation rate, specificity, and a false positive rate. So here is an example here using what's called the receiver operating characteristic curve, or the ROC. So in this case what we have is that we vary the false positive, we vary the threshold between our data set and then observe the number of true positives and true and false positives. So in this case we have a data set, so we have the number of logins that Eve has here, has 20 and so on, and then Bob has these logins here. So is it possible to differentiate Bob from Eve by defining a threshold value on the data? So in this case, what we do is that our metric here, the metrics for the AUC, the metrics for the ROC curve here, we'll take these values and then work out the true positives, false positives, and the threshold values. So the threshold values that we're going to use, or that have been used in this program here, 61, 60, 50, 60, 42, 39, 16. So the ROC curve metrics has calculated these metrics. So if we create a threshold of 61, then actually we get 0 and 0, because obviously 61 isn't going to classify either Bob or Eve as being positive or as being Bob. Now we take a threshold of 60 and we can see here that now we will get one true positive and no false positives. So in this case we now draw the ROC curve for this value of 0.2, and then we have 0.6 is the first value. If we take the 50 now, so the 50 will mean there are 50. We will have a true positive here, and another one, and another one. So there'll be 3 out of 5 for true positives. So we'll get a 0.6 value here. Okay, we can now plot our first point, which is 0, and 0.6, which gives us this point. Now, if we use a threshold of 42, a threshold of 42 means that Eve now has 1 here, 1 and 5, 1, 2, 3, 4, 5. There is a 1 and 5 false positive, because Eve will be identified as Bob here. If we look over here, then we'll have 1, 2, 3, 4. Sorry, we'll have 1, 2, 3, 1, 2, 3. So Bob has a 3 and 5, which gives us 0.6. So we plot our next point here at 0.2, which will give us a value here of 0.6. The next one along is we now take a value of 39 for our threshold. If we see 39, then we'll get 1. But for Bob, we get 1, 2, 3, 4, 5. So Bob now has 100% true positives, and only 0.2, 1 and 5 for Eve will be identified as Bob. So in this case, the true positives are now 1. And if we keep going, then that will be our maximum value that we get here. We then define a metric called the area under the curve. So this will define the quality of the solution and relates to the area which we define here. And we want that to be as close as 1 as possible. So let's have a look at this coding. Okay, so there we go. So we'll just change something. So let's say we reduce this one to 32. Okay, so it should be a worse model. We'll run it again. Okay, so this one here is calculating our ROC curve for our thresholds. So we can see that the thresholds have changed this time, and we can see the shape of the curve is also changing. And down here we print the threshold, and we'll show this as our ROC curve. Okay, so we can take an example here. So our confusion matrix isn't just always one thing against one feature against another. It could be multiple features. So in this case, we have a classification metric model using SVM, using a method of SVM. And what we'll do is we'll try to train on handwriting to be able to identify the numbers involved. So in this case, when we run the code, we see our confusion matrix is like this. So this is a 0, and a 0 is identified as a 0 for 87 times. A 0 identified as a 1 and never happens. Okay, so we actually get a strong score for our 0. As we can see here, our precision is 1.0. If we look at this one, a 1 has been identified as a 188 times, but it was misclassified here as a 0, 1, 2, 3, 4, 5, 6. So a 1 is taken as a 6 here, and we can see here the precision score reduces. If we look at the worst one of all, it's probably this one here, the 8. And the 8 is getting the worst score. In fact, a 9. And 9 is the worst score here. So for a 9, it's identified once as a 1, another time as another number in there, and then 90 times. So our precision value goes down to 0.93. Okay, so in this way we can actually see our confusion matrix and hopefully try and make some sense of it. So just quickly run this example. Okay, so we're using a standard data set in there, sklearn, and we're going to use SVM for our model, and then we're going to import metrics to be able to get the result. Okay, so in this case we run this SVM model and then do our classifications. This is our confusion matrix here. Okay, so let's look at this example here. So in this case, we'll generate some data. So in this case, we'll generate 1,000 points, and there's going to be 2 features. So the data itself will be we'll have 2 features, and then we'll be one of 2 classifications. Then what we'll do is we'll split the data set up into a test data for 30% of the data, and then the rest of the 70% will be used to train our model. So XTrain and YTrain here will be used to train our data set, that's 70%, and XTest and YTest will then be used to test the success of the model. So we'll use random forest classifier here to be able to see if we can classify our data. Then we'll fit the model using the training data, and as a result we'll end up with our data set X test. We take the test data, and then we'll make a prediction using random forest classifier to get this output here. Okay, then what we want to do is to be able to take that data and then score it against our test data to see how well it's matched the predictions. And from that, we'll be able to get our ROC curve and then hopefully show it. And then at the end, we can plot our scatter graph. Okay, so just to show you what this data looks like, this is going to generate our data set. Okay, so in this case we've got 100 data points, and here they are here. So they're classified as yellow and blue. Okay, so this will create two clusters. So our data will be tagged for the X value, the Y value, and then also as say a 0 and a 1 for the clusters which they relate to. Okay, so if we now look at this, okay, so it's the same program. In this case, we'll just save the cluster that we get as a PNG. But when we run this, so when we run this, we can actually see there's our ROC, and we can see the thresholds that we're actually using to be able to create the ROC curve. And there's a whole lot of other metrics that we can actually use. So this is coming in from the model selection, and the metrics element here. So we can bring in ROC ACU curve and ROC curve, but there are other metrics that we can use, such as the F1 score and so on. There's the accuracy score, the confusion matrix, and so on. Okay, so when we're using sklearn, then we can import all of these functions. So the main metrics that we have are typically related to whether we have numeric values or whether we have categories. If we have a numeric value, then we have an R-squared, which is a regression score, and the best value we can get is 1.0. If it's positive, it means that we have a fairly good model. If it's negative, then it's actually worse than arbitrary. If it's 0, then we can predict the output without knowing any of the inputs. Okay, so we vary from +1 down to -1. Anything below 0 is not a good score, and we want to get the R score up as high as possible. The other one we have is what's called the root mean squared error, and that's really taking all the errors between our predicted values. That's if this is predicted and that's actual, it'll take the difference and then square it, sum all the squares, take the square root, and we'll get this value here. Okay, so in this case, here's an example. We can see here this is Bob's login, and then Bob's predicted value here. We can then get an R2 score for the difference between them, and a mean squared error, and so on. So we just have a look at this code. Okay, so there's our R-squared value. It's pretty good in this case. If we now change this, say, to 78 and 6, So we've got 0.95 before, and we can see now we've dropped to 0.64. Okay, so the higher the R-squared value, the better. We want to minimize this root mean square error too. And we can also print out things like the maximum error that we achieve. So let's look at a couple of examples and see how we can understand the structure. So in this case, we're using the diabetes data set. And the first one we're going to do is going to do a numeric prediction. So let's say we had blood pressure and age. Can we use this data set to predict the BMI? So we're going to read in a CSV with that, and then we're going to train the data set on these two features. And we're going to get a result of BMI here. Initially, we'll take a test set of 0.3, so that's 30% will be kept back for testing, and then 70% will be used for training. So take this big data set, and 70% it'll take a random value, a random record, and take the X train and the Y train, 70%, and then they'll keep back 30% for X test and Y test. Next, we'll define our model. We'll fit the model on our training data, and then we'll make some predictions based on the test data to get the predictions, and then we'll compare the predictions with the Y test data to see the difference. Because we use numeric, we'll use an R-squared score and a mean squared error to get the results. So let's give that a try. Okay, so let's give that a try. Okay, so here's the data set that we're going to be using. Okay, so it's defined as a CSV format, and the fields that we're going to be training on, the features, blood pressure and age in this case. So blood pressure here and age here. And we're going to try to predict BMI on this. Okay, so we read in the CSV here, and then we rebuild just a new data set with the two features that we're going to use, X1 and X2, blood pressure and age. And then the one we're going to train for is this BMI. Okay, we just print that data set out, and then we'll split the data set. So 70% will go into the training, and 30% will be kept back for testing. We'll run a random forest regressor, which is a numeric predictor, and we'll train it on our 70% of the data here. And then we just go ahead and make some predictions on the 30% we kept back, and this is our predictions. So we now need to compare that with this, and we can do that through our accuracy score and then through our mean squared error. Okay, so we'll get our scores here, and with our pandas, what we can do is at the very end we can actually have a look to see where our data set is most strongly correlated, to see which of the parameters would be best to train with. Okay, so here is our run, and we can see here we get 0.11, so it's greater than 0, so it's better than no model, and this is our mean squared error. And then at the bottom I've got the correlation factors, so you can see that this one here might actually be a better correlator for X3, which is BMI, so skin thickness. So what we could probably do is find a parameter that wasn't strongly correlated, such as age, and we'll replace that one there, skin thickness. So we got 0.115. Let's see if we can get a better model now. It's much the same as before. Okay, so in this way we can actually start to measure the success of our models. Okay, so there's part of the data set there that we've got printed, and there's 768 rows in there. Okay, so that's for doing a numeric prediction, and we use R squared to be able to see the success of that. So for our next one, we'll now try to predict for category. So in this case, the category is whether someone has diabetes or not. So in this case, we have a field called response, which is a 0 or a 1 to define diabetes or not. So as this is a category, we now use the confusion matrix to be able to measure the success and the number of true positives and false positives. And also we can generate our ROC curve. Okay, so it's much the same as before. This time we're using k-means, which is a clustering method. I'm going to create two clusters with diabetes and without diabetes, fit the model. We predict with our training data for our whether someone has diabetes or not with a prediction, and then we can take our test data, which is the real values, and we can look at our predictions and see what our confusion matrix is looking like. Okay, so let's have a look at this one. Okay, remember the difference between this one and the last one is this is now categories that we're dealing with, and it's a different model. Okay, so in this case we'll do blood pressure and age and then response here. If we look at our data set, we can see here there's response. We have 0, 1, 1, 0, 1, 0, and so on. So it's this we're trying to cluster against. So with two of our features, we're going to train again to see if we can predict the clusters for response. Okay, so same again, we take our data sets, we build it with blood pressure and age, and we're going to see if we can predict for diabetes. So we take our training data, 70% there, because our test data is 30%, and then this is now 30% of the data for our test data. We'll run k-means with two clusters to be able to cluster with diabetes, without, and fit a model. Next, we take our test data, the 30%, and then predict, and we get our predicted values. After that, we can just run our confusion matrix between our predicted values and our actual values and see what we get. Then we can look at our ROC curve here and draw that and get our area under the curve. So let's try and run this model. Okay, so now in this case we're running a clustering model. So we're trying to cluster for whether someone has diabetes or not using two features, blood pressure and age. Okay, so here we go. So you can see here this is the true positives and this is the false positives. So 8 times it predicted incorrectly then. So there is our confusion matrix. Here are our thresholds, and the curve is plotted from these values, and we can see here the area under the curve is 0.478. Not a great result, but we can try different types of clustering and different types of methods to be able to optimize that value. Okay, so this presentation has just outlined a few different classification metrics and a very basic introduction to machine learning.